we know all about probability with replacement. We drew an item, for example, out of the bucket, took it out, dropped it back in, and drew another one. Those were independent events because by returning, in this case, the bear to the bucket, the original probabilities were restored. But what happens if we don't return the first bear that we drew to the bucket? Suppose we have a 25 out of 100 chance of getting the yellow bear. Well, if I draw it out and then just set it off to the side, I now only have 99 bears in this bucket. So there's only 24 out of 99 chance of getting a yellow bear, and there's also only a 25 out of 99 chance of getting a green or a blue or a red. Notice how the probabilities have changed. What happened the first time, because I didn't put this bear back, had a big impact on what could happen the second time. By putting this bear off to the side, I couldn't draw that out the second time. It was no longer free game. We call those dependent events. Remember, independent events are when the first thing doesn't impact the second. Dependent events occur when the first thing does impact the second. And so probability without replacement involves dependent events. Here's a couple of examples just to get you the idea of dependent versus independent events. Here we have Joe. He has 10 pencils. 4 of them are red, 6 of them are green. And he draws one out of his pencil bag, puts it back, and draws another one. This is probability with replacement because he took the first pencil and put it back. Therefore, they're independent events. What happened the first time will not at all impact what could happen the second time. On the other hand, here we have 400 poker chips, and Taurus draws out a poker chip and puts it off to the side. Well, now there's only 399 poker chips left in that box. And because we didn't put it back, what happened the first time had a big impact on what could happen the second time. As a result, we have probability without replacement. Since we didn't replace it, the first event impacted what could happen the second time. We have dependent events. Take a look at this example. This is example number 3. We have 2 cards. We're drawing cards out of a deck. And we want the probability of drawing 2 kings. Now, we're going to draw the first card out, but we're not going to put it back. That's probability without replacement. Because I didn't put the first card back, things have changed. And therefore, we have dependent events. The probabilities are going to change a bit. The probability of getting a king the first time, there were 4 kings out of 52 cards. So 4 out of 52 is the probability of the first king. Now, if I drew that king, there's now only 3 left in the deck. And there's only a total of 51 cards left. And so the probability of getting a king the second time is 3 out of 51. We know the counting principle says that if we get a king and a king, the word and tells us to multiply. We multiply the probabilities, 4 over 52, 3 over 51, and we get 12 out of 2,652, or roughly 0.5%. So it's not very likely that you're going to get a king and then another king. It could happen, though. Now, it's very helpful when you're dealing with probability without replacement to create a tree diagram. The tree diagram really puts everything in order, helps you stay very organized. Take a look here. We have a bag of gumdrops. We have 5 red ones, 2 blue ones. And we're going to reach into that bag and we're going to pull out a gumdrop. And one of 2 things could happen. I could pull out a red one, or I could pull out a blue one. Probability of a red was 5 out of 7. Probability of a blue was 2 out of 7. Now here's where things get a little trickier. Let's suppose I drew the red one out first, and then I ate it. I didn't put it back. Well, what's left in the bag? Well, there are now 4 out of 6 red ones left in the bag. Notice there's only 6 left because I ate one, and there's only 4 red ones. And there are now 2 out of the 6 that are blue. On the other hand, if I ate the blue one, I drew the blue, I ate it, there are now only 6 gumdrops left in the bag. 5 of the 6 are red, 1 of the 6 is blue. And so you can see how the probabilities changed from here to here and all the way through because they were dependent events. If I drew a blue one and ate it, I couldn't well draw that blue one again. Now we'll use the counting principle to write our sample space. We could have gotten a red one and a red one. That's 5/7 times 4/6. 20 out of 42 is the chances of getting 2 red. I could have done a red one and then a blue one. 5 out of 7, 2 out of 6, multiply together, that gives me 10 out of 42. I do the same for the blue and the red, and the blue and the blue, I get probabilities of 10 out of 42 and 2 out of 42. And I use that information to answer the questions that they want me to answer. Let's take a look at some of those questions. The first thing they ask me is what's the probability that both gumdrops were red? Well, that happened in my sample space when I had RR. The probability was 20 out of 42. What's the probability that both are blue? That happened when I had BB. And the probability of that, according to my sample space, was 2 out of 42. Now, we got to think a little bit here because on the third one, they ask us what's the probability that we had 1 red and 1 blue? Well, that happened in 2 different places. It happened when we got the red one, then the blue one. It also happened when we got the blue one and then the red one. And so we have to add those probabilities together. 10 out of 42 times for red then blue, 10 out of 42 times for blue then red, that's 20 out of 42. That gave us a red and a blue. That's the basics of probability without replacement. There's several examples that come up next in the notes packet, and let's take a look at those. I'd like for you to try those and then compare your answers to those that I'm going to put on the screen in just a moment. Example 5 is another example involving gumdrops. We have a bag that has 5 gumdrops in it, 4 yellow and 1 red. It says that Adam will draw a gumdrop, eat it, and then a few minutes later draw a second one. Because he didn't replace it, we have probability without replacement. We have dependent events. The tree diagram shows the probabilities associated with all the possibilities. A yellow and then a yellow and then a green and then a yellow, or a green and then another green. Notice the most interesting thing here is down at the bottom where we have green, green. Because there was only 1 green, it's impossible for Adam to reach in and eat 2 green gumdrops from this bag. Now let's use these probabilities that we've listed over in our sample space to answer some questions. First question is, what is the probability that Adam will eat a yellow gumdrop and a green gumdrop second? Well, that happens when we have the events YG, yellow, green. That's 4 out of 20. What's the probability that Adam will eat 2 yellow gumdrops? Well, that's given by YY, yellow, yellow, 12 out of 20. What's the probability that Adam will have 2 gumdrops of the same color? That happens with yellow, yellow, or green, green. 12 out of 20, or, which is plus, 0 out of 20. There's a 12 out of 20 chance. Finally, what's the probability that Adam will eat 2 gumdrops of different color? Well, that happens when we have YG, yellow, green, or GY, green, yellow. That's an 8 out of 20 chance. The next page, we have a jar, and there are 4 black marbles, 3 red. 2 marbles are drawn out without replacement. And so the tree diagram illustrated here shows the probabilities associated with all the possible events. Black, 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 red, red, black, and red, red. We use those probabilities listed over in our sample space on the right-hand side to answer the questions that follow. The probability for black and black is 12 out of 42. Probability for black then red, 12 out of 42. Probability for red then black, also 12 out of 42. Probability of white then white, well, hey, there are no white marbles, so that's impossible. 0 probability. Probability of at least 1 red. At least 1 means 1 or more. That happened with blue red, red, blue, and red, red. I'll add those three probabilities together, 30 out of 42. And the probability of exactly one red happened with BR or RB, 24 out of 42. Finally, we have two marbles drawn without replacement from a jar. This time we have black and white marbles. We have a tree diagram that shows us the related probabilities. And off to the right-hand side, we have our sample space. We use those to answer the questions that follow. Number one, at least one black. That's 60 out of 90. The probability that they're the same color, that happens with black, black, or white, white, 42 out of 90. Probability of black and white, 24 out of 90. Or the probability of exactly one black marble, black, white, or white, black. We've seen today how we can use probability without replacement, dependent events, and how to work with those probabilities. The most helpful thing, in my opinion, is a tree diagram and listing the sample space.